Testing, testing. Good evening, everyone. Welcome back to our Tuesday evening machine learning workshop live stream. First off, I just want to say thank you to everyone who participated in last week's live stream, last week's workshop, and voted in the Slido poll to help me get a better idea about how I can best serve you in these upcoming weekly workshops. And I want to show you some of the results of the poll real fast. This is kind of how things ended up, which was really interesting to me. The order you see here is order of priority, right? So the numbers on the right-hand side are points that were given to each of these options, right? So you were to rank them from 1 to 5, and if you ranked that thing number 1, meaning your top priority, it got 5 points. Number 2 got 4 points. Number 3 got 3 points. Fourth got 2 points, and fifth got 1 point, right? So the number here on the right is the average number of points. So most everyone ranked EDA and linear regression. These are kind of basic and introductory statistics topics that are still very strongly machine learning related. Was far and away your guys' highest priority. General linear algebra topics kind of was number 2, and then kind of more advanced neural networks topics was last priority. And I figured that the order would either be this or it would be the opposite of this. And I wasn't sure which we would end up seeing, but it looks like we are going to kick things off here in the next couple of weeks by focusing on exploratory data analysis, some core statistics concepts, and linear regression. So in order to help us do this, here's what I thought would be a good idea. This is a Kaggle competition. So Kaggle is a website that hosts machine learning and data science competitions, right? If we go to the competitions tab here, they got all kinds of cool stuff going. And some of these things have cash prizes attached to them, right? So if you go and you use machine learning to fit the best model within a given competition, you could win money. And it's kind of a prestigious thing to be an awesome Kaggler within the data science space. Not a requirement by any means, but it's one of the ways to get noticed and to practice and get better by and large. Well, Kaggle has some competitions on here that they run in perpetuity. Let me see if I can find them. The just getting started ones. And we're going to focus on the advanced regression techniques competition here. Okay. So what this competition is they give us a data set called the Ames housing data set, and it is our goal to predict home prices as accurately as possible using any means we can devise. And they've got some cool systems in place on the website so that we can test and make sure our model is truly generalizing well. In fact, they have this leaderboard here, which shows you how well everyone's predictions are. And you can make lots of different entries to this if you want. Like this person in third place has made 14 different entries, right? And so you can fit your machine learning models, and then they will give you a test data set, and you'll generate predictions on that test data set and submit your predictions here. They'll compare your predictions to this hidden set of true values that they have within the website, and they'll score the quality of your predictions and put you on the leaderboard here in this ranking. And because this competition goes in perpetuity, I believe you can only stay on the leaderboard for up to 3 months. After maybe it's 2 months, but if you're on the leaderboard after 3 months, they'll just take you off, right? So if you were to make a submission right now, you would be compared to anyone who has made a submission in the last 3 months. But I think you should be able to, find yourself in the top 5 to 10% of submissions here. The top score is somebody who probably cheated and found the original data set online and just submitted all the right answers for everything, right? Because in order for them to run this competition, they have to have a big old data set, and then they split it into a train section and a test section. And they use that test section to fuel the leaderboard here, and they give us the trained data set to practice on and to learn about and to make our models better. But submissions are just one small part of Kaggle. One of my favorite things is the discussion and the code sections, right? And so there's some people who will offer really helpful advice about fitting machine learning models. In particular, this code section, I really like to, when I'm working on a specific problem, like the Ames housing data set, to get on and see what other people have done and get ideas for how I can improve my own data science, improve my own code syntax and things like that. And so sometimes reading other people's code is one of the fastest ways I can make my code better and, kind of glean some tips and tricks from what they do and put it in my own tool belt for later. So Kaggle is a cool place. And our goal throughout maybe the next 2 or 3 weeks is building up through exploratory data analysis, basic statistics, and then through linear regression and maybe even some advanced regression models and regularization techniques to really make a kick-butt house price prediction model. And we're going to learn a lot of really valuable stuff along the way. So keep an eye on this. We're not going to use the Kaggle website today. Actually, I take that back. We are. We're going to get the data set from here. But aside from getting the data set, we're going to be just working in our own notebook, exploring, figuring things out, learning about exploratory data analysis today. Next week, we're going to really dive in deep on basic statistics concepts like variance, standard deviation, covariance, and correlation, and really trying to get a really solid understanding of all 4 of those and how they play into exploratory data analysis, but also how they play into linear regression as a tool. And they're all very highly related and super mega important core statistics concepts. So that's some of the stuff we're going to focus on next week. Today, reconnect this runtime here. We're going to focus on exploratory data analysis and a segment of exploratory data analysis called univariate analysis. So there's univariate analysis, there's bivariate analysis, there's multivariate analysis. Univariate analysis means if we just look at one single column of our data, one variable in isolation, what can we learn from it? And so we're going to have a lot of things to do. We're going to have to load our data set. We're going to have to do a little bit of data cleaning. We're going to talk about kind of some of the core differences between univariate and bivariate analysis. We're going to calculate a set of measures called summary statistics. We'll talk about what those are and what they mean and why they're important to look at every time we load a data set and every time we kind of are getting ready to do machine learning. We'll talk about a lot today about analyzing the distribution of variables and what that can, how that can inform us and how that can help us understand the data better so that we can make better data cleaning and data treatment decisions around it. And then a lot of what we talk about today is going to dovetail really well with some things we've talked about in previous weeks, where we talked about the big differences between categorical and continuous variables. In the past, we'd talked about that mostly in the context of our y variable. If our y variable is categorical, we're going to do classification. If our y variable is continuous, we're going to do regression. This categorical versus continuous categorization, to be a little bit redundant there, is going to have a lot of impact on how we explore this data, and primarily the kinds of visualizations that are the most useful to make to help us work with this data. So we're going to talk about what the most common data visualizations, aka graphs, are that we can make for univariate exploratory data analysis. And then next week, as we talk about those core concepts, those core statistics concepts that I mentioned, we're going to also get into bivariate exploratory data analysis, which is probably the more powerful of the two of these. With univariate exploratory data analysis, remember, we're just looking at a single column of our data set and trying to understand it in isolation. But bivariate exploratory data analysis is when we look at the relationships between 2 variables. And in particular, we're really interested in how x variables relate to our y variable. So pairs of variables, pick an x variable from your data set, pair it with your y variable, see if you can figure out any relationships there. And those statistical measures like covariance and correlation that I mentioned are going to be super mega important in helping us do that. And in fact, that is the entire role of linear regression as a predictive model, is helping to model that relationship between the x variables and the y variables. So that's kind of like a little precursor, a little, I don't know, a little sampler of some of the things we're going to be talking about next week and kind of just where we're headed together. Okay. Getting started, we're going to use some of these libraries today. We've got pandas, matplotlib, seaborn. I'm going to add numpy here as well. Oh, and in fact, before I run any of this code here, I want to make sure I share with you. Oh, this is the starter notebook. Share this with you so you can follow along if you'd like. Again, I strongly encourage anyone to type along with me, as that will help some of these concepts sink into your head, and you'll get the code syntax under your fingers and be more comfortable with it. Alrighty. So that's the starter notebook. I guess I'm going to leave this one blank. I'll go ahead and close that so I don't accidentally write in it. And we're going to work in this one. This is going to be the live version that my code is going to be appearing in as time goes on. So I'll share this link with you. This is the live version with Ryan's code. There we go. So that's in the chat now as well. All right. So we'll just import these few tools, libraries we're going to use today. These are really the most common data prep, exploratory data analysis libraries out there. We're going to use them extensively today. Okay. Well, so what is exploratory data analysis? It's the first step in any kind of data analysis or machine learning. Usually we have to do a little bit of data cleaning. We're going to use something called data wrangling, which means we're going to take our data and we're going to have to massage it, affect it, change its shape, work with it in order to get it into a format that we can really understand it, in a format where we can make these graphs and visualizations from it. And we're going to calculate some core statistics to help us really understand what our data is saying to us. We'll call those summary statistics, right? So we'll make graphs. We may have to transform or modify the data set to uncover hidden insights. We'll do that a little bit more next week than we will today, but we'll do a little bit of that today. And above all, probably the most important thing when it comes to exploratory data analysis is something called domain knowledge. And domain knowledge is tricky because you have to work to earn it. It doesn't just come from nowhere. So domain knowledge is basically knowledge about the context that the data set came from, right? This is a housing data set. So the more up to speed I am about the real estate world or housing data or home sales and all those kinds of things are going to help give me a stronger intuition, a stronger understanding of why this data is the way that it is, where it came from, what it's trying to say to me, all those kinds of things. But we can gain some domain knowledge by just doing our own research, distinct from any personal background we may have after we get the data set. So we're going to try and gain what domain knowledge we can together, right? And the thing I really want you to know about this week and the next week is that exploratory data analysis, EDA, is really a subjective process. It requires good judgment, it requires creativity, and we're constantly, as we do exploratory data analysis, doing this kind of internal cost-benefit analysis. And this is something you get better at with more experience, but it's like, how much time am I going to put into doing a certain exploratory data analysis task versus, what kind of benefit do I think I'm going to gain? What better understanding do I think I'm going to gain about the data set by doing that? There may be some things that are like, yeah, I could do that, but I think it's going to be a lot of work. It's going to be, some people say, a long walk for a short drink. So I'm just going to not do that exploratory data analysis. There might be some things we just skip with certain data sets because we just don't think they're that useful. So really, everything we do is up to us as the data scientist. And that's really how everything is in machine learning. Like good judgment and creativity is kind of the name of the game. And understanding the tools we're working with and getting experience doing these tasks with many different data sets and many different situations is going to help us be wise and use our time to the greatest effect, right? So, okay. If I had to break down exploratory data analysis into some basic tasks, to give you kind of a framework for doing this, I would say that it's something like this, right? Get a data set, choose what your Y variable is going to be, divide it into train and test data sets, calculate some descriptive statistics, look at variable distributions, and build some visualizations. And this is a good summary of what we're going to be doing together today, right? So starting with task number 1, get a data set. let's do that. And if you want to follow along with me, you're going to have to do this. So come to this page. I'll drop this in the chat. Kaggle.com/competition/house prices advanced regression techniques, all separated by dashes, /data. Okay. And you'll see a couple of things here that is interesting, is that Kaggle is going to give 4 different files to us. Okay. And these are the 4 files. They're going to give us a training CSV, a test CSV, data descriptions text file, and a sample submissions.csv file. We're going to ignore the sample submission CSV until we're ready to actually submit some predictions to Kaggle. So we won't need that until we've already trained a model, and we want to check and see how well that model's doing. But today we're going to use the first 3, right? So you'll notice that Kaggle's already done step number 3 for us. Divide it into train and test data sets. That's already been done. And in fact, I guess Kaggle's already done step 2 for us as well. Pick the Y variable, right? Because Kaggle says, hey, you are going to predict the sale price of a home. And that's how we're going to grade the leaderboard, right? You're going to fit your model. You're going to generate predictions. You submit those predictions to us. We'll compare them with the true values, which are hidden and held inside the website, and we'll give you a score, put you on the leaderboard, right? So there are some criticisms of Kaggle out in the world that, like, it puts things a little bit too on rails for you, or causes new learners to focus too much on some of the core modeling parts of the machine learning methodology, you know, like the CRISP-DM we talked about. And that's true to some degree, but like, you still have to learn these things. These things are still really important, really core things for us to learn. So I'm not really torn up that they've already done these parts for us. In fact, it probably just saves us a little bit of time. Okay, but in the spirit of trying to gain some domain knowledge, right? We should ask some basic questions about this data set. Like, well, what is the data set? When was it collected? Why was it collected? What was its method of data collection? And then once we actually load the data, we'll look at the shape of the data, column headers, column descriptions, etc. Okay. But what I need you to know is that this data set is called the AMES, A-M-E-S, housing data set. And the reason why it exists is because in machine learning and in the world of statistical analysis, there used to be a really popular data set. I mean, this data set still exists. The data set is called the Boston housing data set. The Boston housing data set was not as big as this data set, but the Boston housing data set contained information about homes in the Boston area, but it also contained some information about the race of the people who lived in those homes, or the proportion of Blacks and African Americans in particular neighborhoods where those homes were found. And some of that was viewed as like, some of that data set was viewed as potentially being used for racist motivations and things like that. And so because of that, the Boston housing data set kind of fell out of favor over time. And a professor, I believe at the University of Iowa, decided, hey, I want a better data set. I want a data set that beginners can use to learn these important techniques, but I want it to be bigger than the Boston housing data set, and I don't want it to have any of those potentially problematic aspects to it. And so that professor created the AMES housing data set. Okay, and you know, in the spirit of gaining, let me scroll down here, gaining domain knowledge. Oh, where do I even have this? I have this way down in the notebook. Like, where is Ames? Does anybody know where Ames, the city, is? This just links to a Google Maps search. Let's look. I type in Ames. Takes me to Ames. Well, there's lots of different Ameses. I want this Ames. Ames, Iowa, right? which is the home of Iowa State University, I believe, where the professor who collected the data set was teaching at the time. Blah, blah, blah. Yeah, we'll come back to the Google Maps here in a little bit. I'm just trying to find the name of the professor so I can make sure I'm not telling you anything wrong. Alternative to the Boston housing data set. I even published it in a paper, 2011. Truman State University. So I was totally wrong. Dean DeCock. Okay. But this is important too, right? This data set was published in 2011. So what do you think is the latest sale price of a home we're going to find in the data set? Well, probably like 2010, 2011. Like, there's not going to be any home sales that happen after that, right? So this data is already 13, 14 years old. But that doesn't mean we can't use it to learn these techniques. It just means that you're not going to be able to take this data set and go and like train a housing data set, train a model that's going to work on today's homes. That's not the context of the data. And so, right, in the spirit of wanting a model that generalizes to new and unseen data, right, I can't take a data set of Ames, Iowa, and then go and use it to make real estate buying decisions in New York or in San Francisco or in Utah or wherever, right? It's going to work best in the context that the data originally came from. But it says specifically an alternative to the Boston housing data set. Okay, so from 2011, it's about Ames, Iowa. What else? So that's the data set. That's when it was collected. That's why it was collected. Method of data collection, this I'm not certain about. But I think in different states, there's usually like a multiple listing service that whenever a home sells, certain aspects about it get recorded. And I believe that this data came from some kind of a service like that. And we'll assume that for now. If any of you learn more about exactly how this data set was collected, let me know, because I'm curious about it myself. So in order to get the data, we're going to need to upload the data to Kaggle here in this files pane here on the left-hand side before we can start working with it. Excuse me, not upload it to Kaggle. We're going to need to upload it to Google Colab here on the left-hand side. We need to download it from Kaggle. So if you're here at the competition, you click on the Data tab. Then if you scroll down, there's a Download All button. You may have to agree to the rules of the competition before it'll let you click this download button. They're just basically things like 1 account per participant, no private sharing outside teams, like don't cheat, blah, 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 stuff like that, etc. Okay, so those are the competition rules. There's nothing crazy in them. Go ahead and accept the rules and then hit download all. And what this is going to do is it's going to download a zipped folder, compressed folder, to your computer. Okay. Once it's downloaded, I want you to right click on it and say open or decompress or uncompress or whatever your computer tasks you to do. You can also just double click on it and it will do that. Okay. And then once you've got just the raw folder here, these are the files that we want. We're going to upload all 4 of these to Google Colab today, but we're only really going to use the train.csv and the data description.txt today. Okay. So you can do that here in Google Colab by hitting the upload button. Find where those files are downloaded to your computer. I'm just going to grab all of them, upload them here. Okay. If you refresh the page here, well, I guess if your Google Colab session ends, you are going to need to re-upload these files. So make sure you keep them in a safe place on your computer. You're going to need to add them back in here. For example, if you were to close this notebook and reopen it tomorrow, you'd need to re-upload the files if you wanted to keep on working with them. Alrighty, so glad we got this. I'm now going to close the file pane here. And we're going to load our data. Okay. Now we are going to load just the train.csv file. All right. So we're going to say df equals PD. We already imported pandas. That's what the PD stands for. Read CSV and then get the train.csv. Okay. We are going to do all of our exploratory data analysis, as it says here, on the train.csv file because we want to guard against something called data leakage. Data leakage specifically from the test data set. Well, what does that mean? Okay. Well, again, reiterating that we want a model that generalizes well, makes quality predictions on unseen data, right? So if I want my model to make good predictions on the test data set, well, I should not let me, the data scientist, or my model look at the test data set. This is something that we did not do correctly when we used the Penguins data set last week. We just used all the data in the Penguins data set. That's because that data set was so small, and so we just used all of it. That was a little bit of a faux pas. Okay. Typically, we want to do all of our modeling and exploratory data analysis only using the training data set. Okay. Any information, right, that somehow gets from the text data set, this is supposed to be the test data set, into our heads or into our model is called leakage. It's like looking at the answers to the test, like looking at the answer key and then go back and studying for the test. Right? It gives you too much information. Right? We want our model to be able to pass the test without cheating, so to speak, without leakage. All right. So we're going to load that. And let's just do df.head, which will show us the first 5 rows. Okay. And it says it has 5 rows and 81 columns. Well, this particular output has 5 rows. The data set has many more rows than that. And as I scroll to the right here, you'll see these 3 dots here, this ellipses in the data set. That is because, well, this data set is much bigger than the Penguins data set, for example. It has 81 different columns. And Google Colab's going, whoa, you really want to look at 81 columns? I don't believe you. That's going to be really wide. So I'm going to truncate a bunch of the ones in the middle. So we're actually not seeing all the columns here. We can force Google Colab and the tool Pandas that we're using here to show us all of the columns by setting something called Pandas display options. We'll do pd.setOption, display max columns, display.max columns. And then if we use none here, that just means show me all the columns, have no limit on the columns. I'm actually going to set this to 100 because we have 81 columns. Hundreds should more than cover us. Okay. And now that ellipses, that truncation no longer exists here in the middle, and I can scroll all the way to the right. And I can see this data, right? So sale price, that's my Y variable. It's all the way over on the right-hand side of the data set. Okay. There's a bunch of interesting stuff about these houses. The type of zoning they're in, the number of feet or yards along the frontage of the property, the total square footage of the lot, whether or not the street is paved or gravel, is the lot shape regular or irregular, is the land contour level or not level, right? Are they public utilities, right? Is the line have a gentle slope? We see all these kind of abbreviations in here, right? And you might scroll through here and go, huh? What is roof mattle? You might guess it's roof material, and you'd be right. But like some of these are like a little bit confusing. What's a really confusing one? None of them are like super crazy, I guess. Pool QC. What is that? Miss Val. What is that? Okay. So there's a lot of kind of funnily named columns here. Okay. And this leads us to one of the important things we should do with a new data set is we should really try and understand the column headers and find descriptions of the different columns. There's a lot of different names for this. Usually there's a file provided along with the core data set that explains what the different columns represent and what the values in those columns represent. And one of the names for this file is called a data dictionary or a data index or a data schema. Those are all synonyms, but they typically give the column names, the data types of the values in the column, a written description of what each column is, the units of the numbers in those columns, They might have information about any missing values, the different possible values of a column, and then any constraints that were placed upon that data as it was recorded. It's not always a discussion of constraints, but the more thorough the data dictionary, the better. Okay, and that is exactly what this data description.txt file is. That is our data dictionary that Kaggle has supplied along with this. So because this is not a session about reading text files, I've already put some code here that will read that data descriptions.txt file and output it here. Right? So pool QC is pool quality, and here's the different values: excellent, good, average, / typical, fair, no pool. So NA values not applicable, says no pool, etc. Okay, and I can scroll through here, and it'll tell me about every single column in the data set. So we may refer back to this. I'm not going to read through it right now because I think that'll just take too long. But this should helpfully remove any confusion around what's going on here. And you'll notice that the column that has the most possible values here, first off, look at all these. How come there's no discussion of the possible values here? Well, because these are continuous columns. They just have numbers in them. Okay? But if there's a categorical column that has been recorded the different categories with string values, well, then there's an explainer about what each of those string values represents. So you can kind of already see there's going to be some continuous values, there's going to be some categorical values in this data set for us to have to work with. And the category that has the most possible options is the neighborhood category, right? The neighborhood of Ames, Iowa that the house is in, and I believe there's 25 different neighborhoods here. I haven't counted it up, but I think that's right. Okay. And that will be relevant a little bit later on. Okay. Now, there's some other odd columns, like, for example, MS subclass, the type of dwelling involved in the sale. Even though this is a categorical value, it has been recorded with a number. 10, 20, 30, 45. I'm not 100% sure why they did this, but this is one type of categorical encoding. Instead of trying to find a way to abbreviate each of these in a way that made sense, they just said, that's too hard. Let's just pick numbers and we'll kind of spread them out. Right? Yeah. So interesting that we have categorical variables, but it is not necessarily the case that every variable that is numeric in our data set is continuous, and every variable that's represented with strings is categorical. That's usually the case, but not always. And particularly with this data set, it's not the case, right? That just because something's numeric doesn't mean it's continuous. Just because, yeah, I guess that's the only statement I can make, right? Just because something's numeric doesn't mean it's a continuous variable. We're gonna have to look at this a little bit more closely to decide what is continuous, what is categorical. And that's gonna be tricky because there's 85 different columns, right? So let's look at the shape of the data set. Okay. 81 columns, 1,460 different properties that were sold. Well, how old is the Hames housing data set? We talked about how it's probably around 2010 or 2011, but we can answer that for ourselves by looking at, what is the name of the silly column? Year sold, month sold, year sold, month sold. I'm looking at my notes. There's so many columns, I can't remember them all, and you won't be able to either. But the more you work with it, the more comfortable you'll get. Oh, I scrolled past it in my notes. Year sold. All right. Year sold. And let's look at what the max year sold is. 2010. Okay. And what was the earliest home sold that exists in this data set? 2006. So these are homes that were sold between 2006 and sometime in 2010. Okay, so about a 4-year period. Which is cool. Okay. We look at the shape of the data. Now here's where we get more into this whole concept of categorical versus continuous and the different data types of the columns. Right? So I can look at the data types of all the columns by calling a certain function. Take my data frame and I say .info. Okay. And it tells me a whole bunch of stuff here. First, I have the column name, the order of the column in the data set, and then the number of non-null values. Non-null values, right? So we saw that the total number of rows is 1,460. Okay, so if a column has 1,460 non-null values, that means there's no missing data in that column. If a column has less than 1,460, then it means there's some missing data in that column, or there has not been any information recorded for that property, for that particular feature or attribute. Okay, and then the data types here are really important. The ones that are already numeric are recorded as int64 or float64. Integers or floats. Those are the ones that are already numeric. Okay. And then the object columns, well, those are typically columns that hold string values. Typically. But that is not always the case. Okay. That's not always the case. Something I want to show you is that there's a few different circumstances for why something could be said to have an object data type in that particular column. Let's see. I'll do another df.head here so we can refer back to this. Okay. Well, if a column is made up of strings, yeah, it's going to have object data type, object. But also, if a column has non-numeric mixed data types, right? If a column has integers and floats, it's just going to show up as a float, because Pandas is smart and it goes, oh, I can turn any integer into a float, and it's just going to say that the column is a float. But if I have numeric and non-numeric data in the same column, it's just going to say, I don't know what data type that is. I'll just call it object, which is kind of this catch-all, right? I'll just say it's a Python object, and really everything in Python is an object, so it's not really telling us very much, right? But it could mean we have a column of mixed data types. It usually, most common means, like 95% of the time, means the column holds strings, but could mean that the column has mixed data types. Now, one particular instance where this can be really annoying is if the person who created the data set has recorded NaN values using a non-traditional indicator. NaN values meaning missing data, right? If any of these values exist in a data set, as it's read in by Panda when we call read CSV, well then all of those are going to get recorded as being null values. Or it's going to say that there's missing data. Okay. But if a person decides to indicate that there's missing data by using a question mark, well, a question mark is not going to get picked up as a null value. It's going to get seen as like a regular string. And so that column will have a data type of object. There's actually kind of a famous data set that has been encoded in this way. It's called the adult data set. And whoever made it decided to record missing data with question marks. And it is a giant pain in the butt, because not only did they do it with question marks, they did it with question marks with a leading space in front of them, which is a nightmare for a whole bunch of other different reasons. But yeah, if a person has tried to record the fact that data is missing using a non-traditional string indicator here that doesn't get caught by Pandas as trying to represent missing data, well then Pandas isn't going to know what to do with it, so it's just going to say, well, that must be a string they want in there. It's an object column. Okay. If a column holds lists of values or dictionaries of values, it'll also have object data type. This is more rare, but it can happen that data sets have lists or dictionaries in them. Or if a column was intended to record a date or a time, or as we sometimes call it, a date time object, which can be not only the date, but it can also have the time after it. If you go, right, that's one, this is 2:23 a.m. on January 1st, 2021. Okay, but this is just the date. So that's either a date or a date time object, usually just generally referred to as a date time object. But if many times if you export a CSV, those date time objects are just turned into strings. Okay, so again, it's a column of strings, but really it's intended that this was a date time object, so we can convert it to that date time object with pd.toDateTime. We don't have any instances of this today, but this can be another thing that happens in your data set. Yeah, technically it's a column of strings, but that's not what was intended originally. It was intended to record time with this totally other different type of variable. Okay, that's another instance. You could have numeric data that's stored as strings. That's again just another instance of it being strings, or even Boolean data recorded as strings. Again, that's just another instance of strings, right? So those are all scenarios under which a column could have the object data type. But I'll tell you right now, it typically just means that column has strings in it, and it's a categorical column, 95, 97% of the time. So, and I haven't seen any instances in this data set where that is not the case. Okay, so that's going to help us because now I can differentiate between these columns, say, okay, anything that has an object data type, that is a categorical variable. And anything that has a non-object data type is probably not a categorical variable. But we've already seen one instance where that wasn't the case, right? We already know that some of the numeric ones are also categorical, right? So all object columns are categorical, and some of the numeric columns are also categorical. Confusing, I know, but this is the kind of nitty-gritty stuff we have to get down to the bottom of when we're working with our data sets. Okay, and it's going to be really important to us because categorical versus non-categorical data is going to be plotted and understood and analyzed in different ways. Okay, so we saw that the data had some null values. 1,460 is the total number of rows. So if I say df.isNull.sum, let's see, what is, oh, I need parentheses on isNull. Okay, it's going to tell me the number of null values in the data set. So this is lot frontage 259. If I come back up to df.info, if I take that 259 and add it to 1201, I'll get 1460. So this is the number of non-null values, whereas this is the number of null values. So it's the opposite. Okay, and we see this funny truncation happening again, but this time it's not happening to columns in our output, it's happening to rows in our output. So I can add another pandas display option so to force it to show me all of the different rows here. I'm going to put that back at the top just because I want it to happen in the same place as I did before. We're going to do the same thing, pd.set option, but this time we're going to say display max rows and set that to 100. And then I'm going to rerun the cells to get back down to where I was. I can do that by holding shift and hitting enter. And every time I hit enter, it's going to automatically navigate me down to the next cell. And if it's a code cell, it's going to try and automatically run it. So I can just hold shift and slam enter a bunch of times. And as long as there's no errors in my code, I'll just get right back down to where I was. Okay. So now we can see we have some columns that have a lot of missing data, like alley, okay, masonry, veneer type, I think that's what that is. Fireplace quality. It's hard to have a fireplace quality if you don't have a fireplace. Pool quality. It's hard to have a pool quality if you don't have a pool. Fence. It's hard to, well, many of these just don't have fences. Miscellaneous feature. I'm not sure what that corresponds to. We'll have to look at the data dictionary. But long story short is some columns have a lot of missing data. And we're going to have to think about how to deal with that as time goes on. Okay. And as a short aside, when we think about missing data, we can really think about it in two ways, right? We can say, well, the data is missing because the feature is NA or not applicable, right? It just didn't make sense to record that value for a home, right? It doesn't make sense to record a fireplace quality if the home doesn't have a fireplace in the first place. It was not applicable, right? So some of these ones that have a lot of missing data probably fall into the category of, well, it was not applicable. Okay. But also there's another kind of missing data where it's the data is missing because it was lost or recorded incorrectly, or the respondent didn't answer all the questions, right? It's just missing. It's just not there, right? And if you think back to the penguin data set, we had some missing penguin sexes, and we had some missing measurements for a few of the penguins, right? I doubt the penguin, was filling out the form incorrectly, right? It was more so that just the scientist grabbed the penguin, they ran off or something like that. They couldn't record any more information about that specific penguin because they all look alike, right? So like that was more missing data more than it was there was a feature that was not applicable. Maybe if there was like a penguin that didn't have a beak or like didn't have flippers, well then maybe it would be not applicable, but that penguin probably would not be around for very long, right? But long story short is, typically data is missing for one of these two reasons, and we might treat that missing data differently if we suspect that the data is missing because it just doesn't make sense to record it, or if the data is missing because it's missing. It got lost, or somebody forgot to record it, right? We might treat those two scenarios slightly differently as we prepare our data. And by the way, we'll never know for sure which of these two scenarios is really the case. We'll just do our best at guessing why that may have happened and use our common sense and domain knowledge to help guide us there. Okay. All right, so you can check another thing off the list. Pardon my scrolling here. I'm getting back up to our list here, right? So we've talked about missing values. Answered all these questions, okay? And what we're going to do with the rest of our time here, which I realize is not much longer, is we're going to sink our teeth into something called univariate analysis, and this may spill over into some of the things we talked about next time. We're going to try and calculate the summary statistics of each of these columns to the degree that is relevant, and these are things like the mean and median and mode, measures of center of that variable, different measures of spread, the variance and standard deviation of these variables. We'll look at percentiles, particularly the different quartiles of our data set. What's the 25th percentile? What's the 50th percentile? What's the 75th percentile? We're going to look at the distributions visually using histograms. We're going to detect outliers using box plots. We're going to look at the distribution of the data using what we call density plots. We're going to build bar charts of the categorical data. We're not going to really use any line plots today for reasons I'll talk about in a little bit. And we're going to use pie charts, which I hate, but everyone wants to know how to make them, so I'm going to show you how to make them, even though they suck. There's nothing a pie chart can do that a bar chart can't do better, in my opinion. But everyone thinks they're so cool because they're circles, I swear. And like every single dashboard, I don't know, statistics, dashboard, Google Images. Every single freaking dashboard in the world has a pie chart on it, or a donut chart. Donut charts, I think, are slightly cooler than pie charts, although almost as worthless. Anyway, look at all these pie charts. They're everywhere. Like everyone expects to see pie charts, even though they are really poor communicators of information. But they're cool because they're circles. Anyway, we'll talk about it. And then next time, we're going to get into bivariate analysis. I have a lot of bivariate analysis explainer here, but we're gonna really go down this path next week. Okay, so let's speed things up here and let's get to it. Back down to where we were. Okay, getting summary statistics with pandas is really easy. I take my data frame and I say, .describe, please get me the descriptive statistics, these summary statistics, and it reports back to me, okay, here's all the different columns. Here's the number of non-null values, the mean, the standard deviation, the minimum, the 25th percentile, the 50th percentile. By the way, another name for the 50th percentile is the median, right? So this is the median, 75th percentile, and the max value. And if I stare at this table long enough, I can learn some cool things. But like we talked about last time, staring at tables is not always the most efficient use of time. It would be cool if we could show these in graphs and we could learn about them faster, if that is, we're fast at making graphs, right? One thing I want to point out, though, is that if I do df.describe, look at this, look at all these columns. This is a lot of columns. Is this all the columns? I don't know, this data set has a lot of columns. Well, let's do .shape on this output here. It says there's 38 columns here. Do you remember the total number of columns in our data set? It's 81, right? So this is not all the columns of our data set. Well, what happened? What happened, right? Well, this set of summary statistics has been calculated on only the numeric columns. If a column has object data type, it is omitted from this output. However, that doesn't mean there aren't summary statistics that apply to the object data type. It's just not the default behavior of this function. If I say df.describe and then tell it to include any columns of object data type, now here's the other 43 columns, okay? But because they're categorical, as far as pandas can tell, there's no way to get a mean or a standard deviation. We have the number of unique values in that column. We have the top, this is the mode, the categorical value that happens most often. And let's see, frequency here is how often the mode appears, right? So 1,454 of the 1,460 homes have paved streets in front of them. Almost all of the homes have paved streets, right? So this is the frequency of the mode specifically. Okay? So again, this discrepancy, continuous categorical, where there's different summary statistics for each of those kinds of variables. If I want to, I can force, is that right? Is that the right syntax? Yeah. I can force pandas to show me everything in one table, but I get a bunch of nans wherever that stat is not applicable. Okay. So this now has 81 columns, but I got a lot of ugly nans in it. So up to you which of those you prefer. I prefer to leave them be separate and just do two different .describes, one for the numeric columns, one for the object columns. Anyway, that's just me. Okay. Another thing that we can do that will tell us something a little bit different is to calculate something called a frequency table. You may have heard of this called a value counts. Again, this is most useful for our categorical variables. Okay. So if you remember, which column was it? Was it MS zoning? I got to look back. This is why we have the data dictionary, but pardon the huge amount of scrolling here. MS subclass. Remember, it's categorical, even though it's already numeric, right? So I could do a value counts on this one too if I want. Okay. And now we'd have to go back to our data dictionary and say, okay, what did the number 20 represent again? What was 70 a stand-in for, right? But this is still a categorical variable, so value counts can tell us something about what the most common subclass is, or what the most common type of zoning is. We can also look at combinations of categorical variables if we really want. This is more of a multivariate thing, but if I can do df.valueCounts, and I can pass it a list of things like MS zoning and Maybe I'll do a street. Okay. Now I've got the frequency of that combination of categorical variables, which is kind of cool. How often was a street have this kind of zoning and paved? Well, a lot, because there's really very few gravel properties at all. Okay. But I can look at the kind of the interaction between those two categorical variables there. Alrighty, and well, maybe I want to do this for every object column in my data set, assuming the object columns are categorical. So maybe I'll do something like this. df.select dtypes, and I can grab every column that has an object data type. There it is, 43 columns. This is only my object columns. And I'm going to save that to a new data frame. I'll call it maybe object df, like that. Okay. So now object df has only my object columns. And I can loop over that. For column in object df.columns, which by the way, object.df.columns is just a list of all the column headers. Okay, here's all the column headers. I'm looping over this list of column headers. So the variable col is going to come to represent each of these different column header strings one by one. And then I can select that column and do value counts. And then I'll get all of the columns, all the value counts of all the columns. Now they're kind of all stuck together here and look a little bit ugly, so I'm going to add another print statement here where I just put a blank line between them, and that'll kind of separate them a little bit more. Okay. And if we had more time, I would scroll through these and we try and make, you know, some assessments. And we don't really have time for that, so I'm just going to leave it to you to scroll through this and see if you can glean any important information about this. A lot of homes have vinyl siding. A lot of homes have brick exteriors and concrete foundations and basements that are in normal condition. I don't know, all those kinds of things. They have gas heating in their homes. Most of them have central air. This is 2006, 2010 we're talking about, etc. All those kinds of things. You can see all that. Now, as we take all of these different features of homes and use them to predict price, in economics, there's a term for this kind of a model. We call it a hedonic housing model. H-E-D-O-N-I-C, like hedonism, right? And that has nothing to do with hedonism. It just means that like the model assumes that each of these different features of a home contributes to the overall value of the home. Now, it may not contribute a whole lot, but having a fireplace may add or subtract from the value of the home. Having a pool or having central air may add to or subtract from the overall value and, by extension, sale price of the home. So that's not a term you need to know, hedonic housing model. It's more of an economics thing, but still, you may see it thrown around in your studying. So just FYI. Okay. Well, now that we think we've got a good understanding of things, we could start to build some data visualizations. And let's make a histogram. And this may be all we have time for today. And I'm going to make a histogram of our y variable, as it is the most important variable in all of this, by selecting the column of the sale price and saying .hist. Okay. It says this funny axes thing at the top. I can suppress that output by putting a semicolon at the end. Semicolons are not a thing in Python, but they are a thing with the plotting library we're using, matplotlib. And then I get a cleaner graph if I do that. Okay. In fact, I'm going to increase the bin size here. That's something I like to do. I like to get a little bit more granularity than the default here. The default does have 10 bins, and I'm going to increase that to 20. Get a slightly smoother graph here. If I increase the bin size to 100, well, that's such a small bin size that it gets even less smooth. But up to you, how many bins you want. All right. And this is a histogram. It shows us that most homes in Ames, Iowa are between, I don't know, $100,000 and $300,000, but there's a few outliers here. A a home that is more than $700,000, these are, in my opinion, pretty affordable homes, even for post housing crisis or during the housing crisis type prices. So, which is again something to keep in mind. We might have that domain knowledge about the time period these come from. Okay. And what I really want to talk about, and this is the last thing we'll talk about here today, and we'll leave. There's a lot more for us to do here, and I guess we'll talk about some of these other things next week. I'll ramble less, and we'll just dive straight in. Is that this particular distribution is something we call skewed. Skewed. Okay. And that means it looks like it's leaning to one side. It's not symmetric. It doesn't have any vertical symmetry. We have this kind of long tail shooting off to one side and a short tail on the other side. We call this skew or skewness. Okay? And one piece of intuition that I want you to take away from today is that typically any variable that measures dollars is usually going to be skewed. And that's because a home is not going to sell for less than $0. We have kind of this boundary on the left-hand side of its range, but the value a home can sell for going in the other direction is unbounded. A home can sell for $20 million, $100 million, right? Which is way off the edge of the graph here, but it's possible, right? So a lot of things that have to do with money end up being skewed. Even things like incomes of Americans graph. Look at this skewed distribution of incomes, right? Because people can't make less than $0. I mean, technically you can go to debt, but that's not included in this measure. Distributions of household income have a similar skew. So lots of things that have to do with money have this kind of skewed nature to them. And we can see that with the histogram. Okay? Now, why is this important? Why is looking at this distribution, why is looking for skew important? Well, because skewness will affect our measures of center. It'll affect our summary statistics, particularly the mean and the median. The mean and the median will always be pulled in the direction of the skew. Okay? Now, what do I mean when I say the direction of the skew? Well, the direction of the skew is wherever that long tail is headed off to, right? This long tail is headed off to the right here, or it's headed off in the positive direction. It's going up. So we say that this data distribution is right skewed or has positive skew or skewness. You can say it either way, right? So this is right skewed or positively skewed. And that's going to pull the mean up above the median. The median gets pulled to the right as well. If there was a perfectly symmetrical distribution, like the normal distribution, this nice bell curve, well, then the mean and the median would both be exactly in the middle. They'd be on top of each other. They'd be essentially the same value. But any amount of skewness causes them to get pulled away from the peak of the distribution. Okay? And we can confirm this to ourselves, right? If I grab just the sale price column and look at its summary statistics, we'll see that the mean is about $181,000, but the median is $163,000. So the mean has been pulled to the right or upwards by, I don't know, $18,000. Is that right? Yeah, it's about $18,000 higher. And that is because of the skewed nature of this distribution, right? So skewness is a thing we want to look out for. And skewness might mean that it is better to represent this distribution or to summarize this distribution using the median, the 50th percentile, rather than the mean. This is why when you hear incomes of Americans reported, right? If you hear somebody talking about the mean, the average income, they're probably misleading you a little bit. You'd rather than be talking about the median income or the medium household income, median household income. That's going to be a better representation of the true center of the distribution. Okay, so mean versus median household income in the U.S. The mean household income was $105,000. The median was about $75,000. It's a big difference. And I'm not going to fact check where those numbers are coming from. I'm just going to trust that Google's AI is not hallucinating right now. And again, a skewed distribution is pulling those measures of center to one side. And that's something we have to be aware of. And if we want to communicate about this data, we want to communicate about skewed data using the median and not the mean. All right. We'll talk more about how we can quantify skewness and some other statistical measures next time. This is where we're going to leave it off for today, which is, I guess we only got to this one kind of graph, but next time we are going to make a whole bunch of histograms. We're going to really get a better idea of how we can programmatically separate our data set into categorical and continuous variables rather than using this object versus non-object data type column discrepancy or discontinuity. We're gonna really kind of quantify what makes something categorical versus continuous. We're going to make density plots, which is a kind of a different kind of histogram, bar charts, pie charts, box plots, and talk about outliers next time. Okay. Do you guys have any final questions for me before we wrap things up for tonight? Okay. If you're typing a question, keep on typing. While I just say, thanks for being here. Thanks for being here tonight. Thanks for following along with this journey. Again, all of these recordings are going to get moved to the Temzee website so that you can easily find all the different ones. I hope to do that sometime this week, and I'll share that with you via social media when that happens, so that if you want to easily go back and find the old recordings, you can find them all on YouTube right now, but I don't think they're going to stay on YouTube forever. And they'll be slightly edited and improved in a couple of different ways. So you might prefer watching them on the Temzee website rather than YouTube in the future. Thanks for being here, and I will see you 1 week from today on the 23rd of July. Thanks, everyone. Have a great evening.